Hello, everyone. Thank you for attending this session and for the opportunity to contribute to IEEE Sensors 2020. My name is Dr. Ahmed Alfadhel from Research Products Development Company, a semi-government commercialization engine in Saudi Arabia. And the title of my talk is Enhanced Properties of Aerosol Jet Printed PZT towards Realizing Flexible Automotive Sensors. This work has been conducted in partnership with Rochester Institute of Technology in the US. So printed flexible electronics are being one of the cutting-edge additive manufacturing technologies that's changing the status quo in the sensing field. Printed electronics is poised to become game-changing additive manufacturing solution that can allow the penetration of electronic intelligence in physical objects. Printed electronics can augment or replace existing manufacturing steps, which leads to reducing cost, increasing flexibility, and even reducing waste. An investigation of new materials and new printing techniques have been ongoing. Despite the amazing development in the field and the great market potential, there are still many material-related challenges and limitations that scientists are trying to address. In this work, we are tapping into processing solutions for ceramic piezoelectric printing that can add huge value to the flexible electronics market in general and the automotive industry in particular. Here we see in the left-hand side a typical interior of a car from the 80s or 90s where everything is let's say, mechanical and simple. Now, when you look in the right-hand side, we see the anticipated automotive interior in the future, digitized interior with electronics and sensors embedded for the comfort of the users. To be honest, we are not far from achieving what's in the picture. As mentioned, the automotive industry is one of the important sectors that shows significant demand for high performance and low-cost materials, while maintaining car mobility and safety. This shift toward the use of advanced, lighter materials and with the adoption of cutting-edge technologies in the 4.0 industry created the need to manufacture cost-effective vehicles with improved performance. In order to be able to achieve the goal of designing smart cars that connect with the user and interact with the surrounding environment, the integration of high-performance, reliable, smart, flexible sensors into the car's body would be required. Traditional sensors and electronics suffer from limitations in the automotive industry, constraining the design options and the intelligent function effectiveness. Processes such as in-mold electronics have shown great potential to integrate electronics with composites, offering unique capabilities for the automotive industry. When we say in-mold electronics, we refer to printed electronics on flexible substrates which successively undergoes a thermoforming and an injection molding process to form a 3D functional, fully integrated part. It's anticipated that in-mold electronics can become a market larger than $750 million by 2028. In-mold electronics is ideally suited to quickly develop intelligent surface solutions with the ability to integrate electronics, sensors, and interfaces. Main limitations from the printed electronics aspect is the ink technology. New functional ink chemistries and printing processes are being developed. And then when we look at printing of piezoelectric ceramic materials in particular, we have a challenge with temperature processing, and researchers have been looking into that. So piezoelectrics can be utilized in automotive to realize high-performance devices such as touch, pressure sensors, long and short range radars, and energy harvesters if you are willing or if you are able to establish these kind of flexible devices. So in this work, a photonic sintering method was presented by using repetitive high-intensity sub-millisecond flash pulses of an aerosol jet printed lead Zirconate Titanate, or PZT, Nano-ink, to achieve high-quality sintered devices. The rapid processing results in enhancing the piezoelectric properties compared to the conventional thermal sintering process. The presented process allows the realization of high-performance, fully printed, flexible piezoelectric sensors on temperature-sensitive substrates for several applications. If we look in the picture in the left-hand side, there's an illustration of the process that we've been conducting, starting with printing, going through sintering, and then ending up with the functional device. Aerosol jet printing technique was used to produce the PZT films. This technique is capable of depositing inks having a wide range of viscosities up to 1000 centipoise, enabling high-density PZT deposition. Aerosol jet is different from the well-known inkjet printing, which is more challenging when it gets to printing nanoparticle-based inks or high-viscosity inks. So PZT nano inks was prepared from particle-based powder and solution medium, and by reducing the particle size and adding the sintering aids, we lower the sintering temperature. We have the larger surface area that results in higher surface energy, or the high surface area of the smaller particles that results in the higher surface energy, which is the main driving force in the sintering process. Also, by having the small particles, we can increase the packing of the film, of the PZT in the film, and the liquid phase aid act as a lubricant and assist with the reorientation. The optimized ink solution can be seen in the table on the bottom right-hand side. Stainless steel foil, capable of withstanding PZT sintering temperature, was used in this process. And that's both for photonically sintered and thermally sintered samples. In definition, sintering is a high-temperature process that is used to densify PZT powder in order to enhance the electric and mechanical properties. Conventionally, PZT is sintered at temperatures larger than 1000 degrees Celsius and a duration longer than 1 hour. This exceeds the melting point of commonly used electrode materials and, of course, flexible plastic substrates. PZT film was photonically sintered in this work under an ambient atmosphere for a very short period of time. And a xenon lamp was utilized that emits broadband sub-millisecond high-intensity pulses that control the heat which is exposed to the film. The traditional thermal sintering in a high-temperature furnace was also carried to provide the sample for comparison at 1000 degrees for 1 hour. COMSOL, our finite element thermal simulation, was conducted to actually get an idea about the heating of the obtained heating at the top side of the sample and then the interface. And it was noticed that by the 1 millisecond pulses for a period of 30 seconds, 2 cycles, we obtained 1000 degrees heating at the top surface, while only going at lower temperature than 800 degrees at the interface. And by having the very short spikes, we limit the potential for substrate melting due to thermal response times. And there is, of course, room for even improvement. And the range from 800 above has been also demonstrated to be sufficient to fully sinter the film, which is what's required to obtain the maximum performance. Polling is an essential post-processing step for the PZT device to reorient the dipoles. For conventional ferroelectric materials polling, electric field is applied across the films at elevated temperatures below the Curie temperature to increase dipoles mobility. A possible approach with the rapid sintering in this work is conducted by polling during the sintering process without applying the extra annealing step. So repetitive pulsing of the photonic lab provide the appropriate total energy and pulse profile to anneal the material, facilitate the dipole reorientation, and enhance the piezoelectric properties. The voltage was applied between a top transparent electrode that allows flashlight penetration and the substrate that acts as a bottom electrode. It's observed that from the higher pressure sensitivity test, from the pressure sensitivity test, that we obtained higher sensitivity with the photonic and Pauling process compared to the conventional Pauling as a separate step. So in the case of thermal sintering, oxidation was evident as a loss of metallic luster and a resistivity increase, and that was not a problem with the photonic sintering, and it's obtained with the resistivity test. The extremely short processing duration prevents significant oxidation from occurring. An additional influence on the thermal sintering film properties is the high furnace sintering temperature and duration that leads to the release of the lead oxide and the formation of the pyrochlore phases, which results in a weaker piezoelectric properties. The short pulse duration of the photonically sintering process prevents the formation of the pyrochlore phase and contributes to the improved properties. Scanning electron microscopy images of the PZT films, top side and cross section, were captured as a qualitative measure. So prior to sintering, the particles were uniformly distributed in the film, you see on the left-hand side. After photonically sintering, they are more fused together and even with better and smoother performance compared to the thermal sintering. There are few cracks that can be actually improved in the future by adding nanoparticles with sol gel PZT or adding crack bridging additives such as platinum. And the XRD plots, they actually are indicates of the pyrochlore phases with the left-hand side for the thermal sintering and the right-hand side for the photonic sintering. The polarization electric field hysteresis loop is a key tool to study the ferroelectric properties of the PZT material. The ferroelectric properties that was obtained summarized in the table, and you've seen in the ferroelectric loop, the black curve for the photonically sintered and then the red for the thermally sintered. We can see clear distinguish in the performance. High remnant polarization was obtained in the photonically sintered film, reflecting better ferroelectric properties than the thermally sintering group. Superior piezoelectric voltage coefficient and the relative permittivity values were observed in the photonically sintered films. This indicates that photonically sintered PZT would have better piezoelectric response and higher charge storage capacity. Qualitative observations and quantitative measurements show enhanced piezoelectric properties and successful sintering of photonically sintered PZT film when compared to the thermally sintered film. The enhanced properties observed in the photonically sintered film can be attributed to the rapid photonic sintering process that prevents oxidation of the substrate, which adds an extra dielectric layer in the system. The piezoelectric voltage coefficient G33 was measured using a pneumatic cylinder compression system, and then the output pressure has a direct correlation with the input signal voltage, and it's applied to the cylinder that applies force to the PZT device as illustrated in the testing setup. So in conclusion, aerosol jet printing for nanoparticles-based PZT with photonically sintered have demonstrated superior performance in a very limited time with an ambient environment processing. The enhanced characteristics were demonstrated with the photonic sintering, and it's compared to the thermal sintering process. And the main two issues, which is the oxidation and the pyrochlore phases, it seems to be eliminated and they negatively affect piezoelectric properties for the thermally sintered film. Due to the extremely rapid pulses that result in lowering the temperature increase in the substrate, the reported photonic sintering process opens the possibility of directly fabricating PZT films on common electrode materials and flexible substrates without needing complex film transfer processes, facilitating the realization of flexible piezoelectric devices for the automotive industry. Thank you very much.